All right, don't worry, guys. We got a one pager. It's going to be pretty relatively simple. I'm going to talk about both ways on how to do it. Remember, how do you guys feel about geometry? Okay. All right. So let me show you. And if you don't want to do it this way, you can continue to do it the way we did it yesterday. The circumference of a circle is 2 pi r, and circumference means the distance all around. So this in red, that's your circumference. And one revolution is equivalent to 2 pi radians. It's just this formula. See, that R stands for radius, which just means radians. So 1 radian is literally whatever the radius is. That's what we mentioned 2 days ago, right? Because I saw you guys Wednesday. And then I say, so for example, when a wheel does 1 revolution, the distance it covers is 2 times pi times radius. So if this were the ground, if I were to have that wheel here on the ground, and this does 1 revolution, the amount of distance it covers is literally just 2 times pi times radius. Does that make sense? So here's how you can use that information. Okay, child, you're telling me this. How can I use that? For example, what is the linear velocity of a wheel spinning 5 revolutions per minute with a radius of 20 inches? Method 1, you can do it like this. You can write 5 revolutions. You're still doing that little T-chart per minute. So there's just like a long fraction. And then you can say, in 1 revolution, you cover how much distance? 2 times pi times 20, and then put the word inches like that. And then revolutions cancel out, and you get an answer. What's your answer in inches per minute? So all you do, you take your calculator, and let me clear this. I'm going to push alpha y equals. I guess you don't need the alpha y equals because there's nothing in the bottom, just a 1, but I already typed it in, so too bad. 5 times 2 times 20. 5 times 2 times pi times 20. 5 times 2 times pi times 20. Oh, I didn't put a 1 in the bottom. Silly me. Put a 1. Boop. And there it is. 628.3185. 628. And I already forgot short-term memory. 3185. Thank you. 3185. And then what are my units? Inches per minute. Yes.
When we're doing or whenever we get the answer and we're rounding the fourth decimal place, do you want us to round up if there's a greater number next to it?
That's a really good question, miss. You can choose to round up, or there's a word called truncated. Did I tell you guys about that word? Yeah, that means just whatever the digit is. So this is why I kind of like more than 3 digits. Just put more, 4, 5, 6. It doesn't, you know what I mean? If you have a calculator, just put all the digits that you see in the calculator. That's a safe route. You don't have to do it like this if you don't like it. Like, Chab, I don't like it. Okay, how did we do it yesterday or 2 days ago? We did it like this. Look, notice you're going to get the same answer. So I'm going to put 2 here to showcase that we're going to get the same thing. So you start with the same, 5 revolutions in a minute. Chop, this is how we did it 2 days ago. In 1 revolution, we went from revolutions to radians and then finally to inches. In 1 revolution, how many radians are there? So I write 2 pi and I put the word rad for radians. And then I go in 1 radian, that literally means what the radius is. What's my radius? 20 inches. And look, it's the same. It's the same computation. 5 times 2 pi times 20. Do you guys see how it's the same? 628.3185 inches per minute. How do we feel? All right, let's see what it says. What is the angular velocity? Oh, okay. Well, the angular velocity, I'm going to put a W. If they don't give me units, see how they didn't give me units? If they don't give me units, you just say angular velocity is 5 revolutions per minute. 5 revs per minute. All right, what else? How many different ways can we express the angular velocity? Okay, how else can we express the angular velocity? We could express it in radians per minute. So I can go 5 revs again per minute. And in 1 revolution, there is 2 pi radians. There it is, revolution. So now we have radians per minute. Do you guys see that? So W equals, I come back. You can say 10 pi. I guess you know what, that would be the perfect answer. 10 pi radians per minute. That's a pi there and then RAD. Or you can say, let's see, what's that? 31 point. How many digits of pi do you guys know? 10 pi. 31.4159. 31.4159 radians per minute. How else could you express it if you wanted to? You don't have to. If you wanted to, you could express it per second. I'll just extend it one more time. In 1 minute, there's 60 seconds SEC. So let's see what that is. So I'm going to just take this number and just divide by 60. 0.52359. Let's see. 0.52359 radians per second. So look at all the different ways. So I don't want to say there's infinite amount of ways, but there's if they don't tell you what units to use, angular velocity is just how fast something's rotating. So as long as it's degrees, heck, I could have put it in degrees if I wanted to. Degrees per second, degrees per minute, degrees per hour, radians per second, radians per minute, radians per hour, revolutions per second, revolutions per minute, revolutions per hour. So many ways. Cool or not cool? All right, we're done with that. And how do you feel? Do you feel okay? What's up? Angular velocity is how fast something rotates. Linear velocity is the distance covered over time. So should I write that somewhere here? Angular, arrow is rotational speed. Rotational speed. Linear, and I'm talking about velocity, is distance divided by time. Where distance is like meters or miles or kilometers. See, kilometers per hour, miles per hour, meters per second. You see the difference? And an angular velocity is how fast something rotates. Revolutions per second, revolutions per minute, radians per second, anything to do with rotations. It could be degrees. We haven't been working with degrees lately. That's on purpose by design because when we take our AP exam, everything's going to be in radians. That's not to say that there's no degrees. Eventually we'll do it once we're like super beasts, but we're not there yet. We're close. We're one more day away from that. How do we feel? We feel okay? All right. Don't worry guys, we're done. Don't yawn, that's a demerit. Two rotating objects connected by an axle have the same angular velocity. YouTube, I don't give demerits for my kids if they yawn, so don't thumbs down me. Okay, so do you guys know what an axle is? I mean, I guess this could be an axle because it's a cylinder. So what it's saying, two rotating objects connected by an axle have the same angular velocity. Okay, let me try and draw. Guys, full disclosure, I got a D in art, so I don't know how good my drawing's going to be. So let me draw an axle. Here's my axle. And I'm going to put a big wheel on the left one. And I'm going to put a little wheel on the right one. I tried to make it three-dimensional. I don't know if you can tell. Is that a good job of an axle? All right, so there it is. That's an axle. So if this axle does one revolution like this, if I'm spinning that axle and that does one revolution, the big circle does one revolution and the little circle also does one revolution. No, well, the way I have it here, right? It does one. So anytime the axle does one revolution, both the big and the little do one revolution. Does that make sense? So that's why it says here, look at this. Two rotating objects connected by an axle have the same what? Angular velocity. Now the linear velocity is different. The distance that the wheel covers is different. Obviously the bigger wheel covers more distance, but the angular velocity is the same. Does that make sense to you guys? Yes. Perfect. Now look what it says here on this one. I just got the chills. It might be all this cold air. I don't know. Two rotating objects connected at their rims have the same, okay, look at that. Linear velocity. Shav, I don't know why. Why do they have the same linear velocity? Let's do a drawing because you guys are visuals. I'm going to draw a little circle. And I'm going to draw a big circle. I tried. Yeah. If this is spinning this way, this one's spinning this way. Yeah, Kilgore loves this stuff because of robotics and reasons. Show Kilgore this. As a matter of fact, I'll send her a video. Well, okay, you guys tell her first. All right. Look at this, guys. Obviously, the angular velocity is different. The angular, if the big one does one revolution, that little one does a whole lot more than one revolution. We got that. But the linear velocity, if the big one is covering, let's say at the exterior, if the big one is covering 5 miles an hour, then the little one, because they're touching, is also going 5 miles an hour. Does that make sense? So notice what I have here. If the two objects are connected at the rims, then what's the same? Linear velocity. This is also similar This is similar to two wheels connected by a belt. Remember the bike problem?
Yes.
So if they're connected by a belt, if this one is spinning at, I don't know, I'm just making up a speed, 5 meters per second, then the little one is also spinning. Well, I shouldn't say the word spinning, the linear velocity. Then the linear velocity of the little one is also 5 meters per second. Does that make sense? So maybe I should put also here the also with belts. Also with belts. So they're the same. It's the same idea. How are you feeling? Okay. Do you guys feel like an engineer yet? All right, turn the page. Look, you're now a mechanical engineer. Good, congratulations. You can be a mechanic. Show your guardians all this cool stuff that we're doing. Is anyone's parents a mechanic? None of y'all's parents are a mechanic. Dang. Or your dad's an engineer. Sure, dad, all the activity with all the wheels and all the belts. Like, look, dad. As a matter of fact, tell your dad to help you with your homework. Hey, do this, dad. I bet you he'll do it like a boss. All right, you guys ready? Here we go. Two pulleys are connected by a pulley belt. So there it is. That's just a pulley belt. When you open up the hood of your car, that belt is called a pulley belt. Or sometimes they just call it a belt, right? The small pulley has a diameter of 10 centimeters. So this small pulley here, that has a radius of 10. Oh, that's the diameter. So the radius is what? 5 centimeters. Let's see. The small pulley of the diameter 10 centimeters and rotates at 100 revolutions per minute. Okay, so this small one is going 100 revolutions per minute. Find its angular velocity in radians per second. Okay, we can do that. So start with what they give you. 100 revolutions per what? Minute. And what do they want? They want what? Radians per second. So you're going to cancel out the radian. Bless you. You're going to cancel out the revolutions. Sorry. So you're going to write 1 revolution in the bottom. In 1 revolution, how many radians are there? So write 2 pi rad. Make sure to put units. So right now, look, the revolutions cancel out. Let me slow down. And you have radians per minute. Is that what I want? No. Almost. I want what? Radians per second. So continue the T chart or whatever you call it. And I'm going to write, since I want to cancel out the seconds, I need to have a minute on the top. So 1 minute is how many seconds? 60. So now the minutes cancel out, and there it is. Whatever you have in the numerator, multiply. Whatever you have in the denominator, well, if you had several, multiply them, and you're going to divide. I'm just going to use my little fraction feature, so I never get it wrong. Alpha y equals enter. And I'm going to type 100 times 2 pi divided by 60. So 100 times 2 pi. And then I'm going to put a 60 in the bottom. And I got 10.4719. Is that what you got? Yes. The more digits, the better. Equals 10.4719. And I need units. Yeah, you can put more. I stopped there. I like the 4 digits after the decimal. But if you want to put more, that's fine. You just need 3 digits after the decimal. But how do we feel, guys? Okay. Find the linear velocity of a point on the rim of the 10 centimeter pulley. Okay, so that means they want the linear velocity of right there. That rim is touching that belt. Do you guys see that? All right, so here we go. I guess we can start with this. Do you guys want to start with that? 10.4719 radians per second. And in 1 radian, what's my radius? 5 centimeters. Radians cancel out, and look, that's centimeters per second. Is centimeters per second a linear velocity? Yes. So take that 10.4719 that you have in your calculator, don't round it, just like there it is, and just go times, was it 5? Times 5. And there it is. I got 52.3598. Is that what you got? You can round it if you want to 99. So let's see, 52.3598. Let me put one more digit just for kicks. 987. I'm doing it truncated. And what are my units? There it is. How are we feeling right now, guys? All right, go to the next one, letter C. Find the linear velocity of a point on the belt connecting the 2 pulleys. Well, do we already have it? Yes. this small pulley is what's driving that belt, and that since that pulley is driving that belt, that sorry, I can't talk today. 52.3598 centimeter per second is what's on that rim of that pulley, so that belt is going the same. So I'm gonna write same as in B, comma, and then just write the number 52.35987 centimeters per second. Are we okay so far, guys? All right, letter D. Find the linear velocity of a point on the rim of the large pulley. Okay, now they tell me the diameter of that, which is the diameter of 30 centimeters. So that means the radius is how much? 15 centimeters. So there it is, 15 centimeters. So see, find the linear velocity of a point on the rim of the large pulley, which is okay, linear velocity. Because of the belt, what is the linear velocity? On the same, perfect, right? Same as in B. Because of the belt, guys, the belt is going this speed, and the belt is driving that large pulley. Does that make sense to everyone? Okay. Yeah, they call this a pulley, and that large circle is a pulley. Same as in B. 52.35987 centimeters per second. How do we feel? Okay. Letter E. Find the angular velocity of a point on the rim of the 30 centimeter pulley. Okay, we can do it one of two ways. Maybe we'll do it both ways. Do you guys want me to do dimensional analysis, or do you guys want me to do it with geometry? Okay, I'll show you with geometry as well. You're going to see it's going to be the same digit per digit. So start with what you got. 52.35987 centimeters per second. And if you want to get the exact same answer, like the perfect answer with the geometry, use all the digits. And in this one, I'm looking at the large pulley. In 1 radian, what's my radius? That's what I'm going to use. So I'm going to go in 15 centimeters. That is 1 radian. And there it is radians per second an angular velocity. Centimeters cancel out. Take your calculator. And I'm going to go put, there it is. There's the answer. So I'm going to push divide 15. That way you have the exact answer. So let me make sure I did everything correct. Yep, divide by 15. Bam, 3.49065. 3.49065 radians per second. Okay, you could have used geometry. I'll do it right here. I'll do it in a different color. Second, I'm going to write using geometry. You could have done this. You could have done a scale factor. Use scale factor. Chav, what do you mean scale factor? Well, the radius of this one is 15. The radius of this one is 5. So I could have done this. I could have gone 15 divided by 5. That is a 3. So that's my scale factor. What that means is every time this little circle does 3 revolutions, this big one is doing 1. Or I guess you could say the other way around. Every time the big one does 1, the little one does 3. Does that make sense? So I could have taken, I could have taken this number, or where are you? Where's my radians? This number right here. 10.4719, and I just divided by 3, and I bet you I'll get this number. So look, watch. I'm not fake. You see that number, 10 point whatever? Look at this. Take that, divide by 3, and let's see if we get the same digit per digit. And look at that. Child, the last digit's off by 1. Relax. It's because of the rounding. But look, it's the same. Isn't that cool? So as long as you know what you're doing, see, this is what I'm talking about, guys, critical thinking. Too long, and I'll stop because I don't want to preach forever. But guys, I hope that you're not going through the motions in your science classes and your math classes in the past. Because you went through the motions, that's why we have issues today. It's okay. It is not too late. You're still here. So let's try your hardest to use critical analysis, to use critical thinking, like how is everything connected? And if you do it this way, you'll never be wrong. Are we starting to open up y'all's minds a little bit? Okay, hey, no yawning, that's a demerit. Yeah, that's a demerit again. I'm gonna write everyone up. Okay. All right, last question. Find the angular and linear velocities of a point at the center of the 30 centimeter pulley. Okay, well, the angular velocity, I'm spinning that speed on my big pulley, no matter what, all the time, the same, no matter where you're at. What's up, bestie? Thank you. I appreciate you, miss. You're the best. So the angular velocity, guys, is going to be the same everywhere. Does that make sense? So I'm going to write angular velocity, 3.49065 radians per second. Yay or nay?
Okay.
Okay. Now they want the linear velocity at the center. So I'm going to write V for linear. At the center, have you covered any distance? No, you're just spinning. Chop, what do you mean when you always say cover distance? Well, if I was, imagine you're a bug. If you're a bug at this location, bird's eye view, you would cover all this distance as it rotates. So that's what I mean. The perimeter of that circle. Does that make sense? So if I'm in the center, there is no circle. You're just spinning. But you're not covering any distance. Does that make sense, guys? So what is my linear velocity in the center? 0. And you got to put units. It doesn't matter. In this case, it doesn't matter what units, because 70 per second is the same thing as miles per hour, same thing as kilometers per hour, because it's 0, right? As long as you have a unit of distance divided by a unit of time. How do you feel? Do you understand how all the little intricacies work? Okay, you got about 12 minutes. Maybe you'll be able to finish it if you're fast enough, but I think we should be able to get halfway through the activity. Use your group. And yes, it's okay. You can turn it in Sunday on Canvas if you don't want to turn it in today. But that's it, guys. And I'm here, so you can ask me questions.